Hi everyone, this is my master thesis slide presentation about my master thesis project called 3D electromagnetic Finite-difference time domain method FDTD acceleration using cellular neural network array over a parallel system. My name is Juan Mayor Torres, electronic engineering from Pontificia Universidad Javeriana, Cali, Colombia, South America. Okay, to enhance the presentation, we made some outline to do this. Is about 8 items. The first item is a problem statement that we are talking about first. The second one is a scene background. That is about the cellular neural network theoretical basics. Third one is the Maxwell PD mapping with a dispersion model that is attached with them. And the fourth one is the broadcasting strategies that we are trying to describe here in order to describe the parallel process that we made here to enhance the implementation possibilities in parallel implementation, of course. And the MPI results in the 5th item that shows that results specifically. The 6th is the transient results, and the 7th is the conclusion of the future works. Okay. The 8th one and the last, the bibliography, is about all the topics that we're going to talk here. Okay, let's see. Well, the problem description is about a solution or a particular solution of FDTD numerical approach over a particular application that is resonant cavity. Okay, the resonant rectangular cavity that is surrounded by a PC environment or a perfect electric conductor environment within only one electric dipole, okay, as a source, as an electric source. To take this, we define 2 specific objectives around this. One is the measurement of 2 different broadcast strategies, that is the binary tree and the filing model. And the other one is the analysis of the mathematical dispersion implied on the FDTD algorithm, and obviously implied on the specific application that is the resonant cavity. Okay, this is the main landscape, or the main overview of or on problem. Okay. Okay, let's see. This is the problem design flow. And we describe here the possibility to give the user some cavity parameters that they have to give us an input. The input will be parameters that are implied in the material, in the time stepping, in the spatial domain, density, whatever. That could define the cavity, of course. That is the specific application. And the Octave app receives to invoke some EM simulators, as you see in the figure, and of course try to create a user plain text that is using to connect the CMPI app with the EM simulator results, and finally give the possibility to the user to give an evaluation or a numerical error comparison between the FDTD custom implementation and the EM simulator implementation. Okay, this is the general design flow for the problem and the possible solution for us. Okay, let's specify this in the later sections. Okay, to begin the theoretical background, we start with the CNN schemes. Okay, if you can see here, you can see 2 common schemes with different pathways that connect the different amount of PEs around it. These PEs are processing units or processing elements that could process a variety of this number of G cells that are implied in the computational domain. This is 2D, but it could be extended to 3D. And these cells could be defined as the following slide. As we can see, you can see in the upper circuit a model that is about the artificial neural network. As you can see the weights and the inputs and some operator with the bias and the functional and the activation function here in the output. But in the last part, you can see a circuit that is describing the cell itself, then the cell could have a linear model in terms of the differential equation that could allow you a map or a direct map between the parameters implied in the circuit and the PDE that is desired to be mapping. Okay, and these dependent current sources are totally dependent on the nearest neighbors per each cell that we can study specifically. Then all of these dependence depend on the state value of every other neighbor that are near to the cell. This is the most important value, the most important characteristic. Then this equation 1 is the main description of this. And here we are with the parameters. The parameters are t at the time it's stepping, the x0 that is the state variable, the k that is the neighborhood matrix, and the k that is the nomenclature of the dependent sources, Bj that is the matrix that depends on the initial value, the previous values per each cell, and the e-bias that is a DC component that is related with the ANN topic, but for us it's optional. Then if we neglect the value of the e-bias or the DC component, you can arrive to equation 2. That is the generalized part of this approximation per every cell in the array. Okay, let's continue. Okay, then to get a great mapping between the CNN and the PDE specifically, we have to define the PDE. Then the PDE would be the Maxwell basic PDE that we can see here in the 3 and 4 equation, and we could have the 3 and 4 equation per each axis. Then if you analyze this, we can see that only H and E fields depends on time in terms of the upper index, but in the other cases would be analyzed between any other kind of axis. And you can see another parameter as mu, sigma m, there is the permeability magnetic and conductivity magnetic part, and epsilon, that is the permittivity electrical, and sigma e, that is the conductivity and electrical part. Okay, this is the most important approximation, or that is discretized type of Maxwell PDE equation. Okay, and if I want to map this kind of equation, we can arrive from a generalized model of CNN. Then if you can see here, we can define a matrix A as a matrix that are involved with the initial value or the inputs UK, as you can see in the figure in the equation, sorry, and B is a matrix associated with the neighborhoods outputs, and that is in the case this XK value is approximated with the E or H fields that are related with the neighbors. In this case will be the boundaries per each cell. Okay, and finally the XY, that is the state value per each cell approximation. The inner value is the number of nearest neighbors per every cell. Then depending on the pathway, you can obviously calculate what is the number of neighborhood around each cell in the particular application. For a case, we can only left, right, up, and down. Okay, in 2D. In 3D, we have 6 neighbors, of course. Well, to continue this, we have the CNN matrices. The CNN matrices are the particular matrices A or B that are obviously related with the Maxwell PDE basic mapping. As you can see, the under suffix is the suffix that are related with the A or H field, or J or M source. There is in this case J is an electric source and M is a magnetic source. And as you can see, this matrix only have one value, that is the center value. And this value is related only with a temporal displacement, not with a spatial displacement. Then any other kind of matrices implied on this could have only a displacement in time. If you can do a displacement in the space, you can put values around the matrix, not only the center. Okay, this is the most important thing. As you can see, you can see this behavior in the next slide with the matrix B and BA and BA in theta on y-axis, and you can see the center value is 0, but the values around up, down, and left, right are different to 0, and these values are totally related with the curl operator. Then the curl operator gives you the possibility to derivate the equation, the Maxwell equation, in different kind of axes. In this case, if you have the zeta axis, you can derive this in y and x axis, as you can see in the lower part of this division, delta x in the case of x and delta y in the case of y, and whatever. You should have the possibility to take a matrix B E in terms of y and matrix B E in terms of x and whatever and so on. Okay, this is the way that you can see this kind of behavior. Well, and to make a compound of this complete mapping, you can arrive to equation 8 and 9. The equation 8 and 9 are describing particularly the possibility to have this Maxwell PDE for each axis, in this case theta, in terms of x and y, obviously related with the curl operator, and giving the possibility to express the equations in terms only the matrices. Then you can solve all these components in terms of y and x axis too. You can take all this figure that is a compound of 3D structure of G cells that should be solved by another compound, another subdivision of cells around the array. Okay, this is the most important approximation. Okay, if we have the right mapping with this, we can arrive for a particular application, that is the cavity model. Then the cavity model are totally related with the resonant model. We can see here there is some expression that is a totally harmonic part with a particular expressions that are depending on the dispersion harmonically. Then if you can change this part, you can change the component that are related with the sinusoidal and cosinusoidal part, and you have to avoid it in order to get a great implementation of the FDTD algorithm. Then if we analyze the curl operator, taking this kind of expression into account, we could arrive to expression 11 that are totally linearized by a term that is depending on the dispersion per each axis. Then we can relate the expression per x-axis with the stability condition in terms of zeta axis. There is this component here, and every pole in this zeta axis, in this zeta domain, should be inside the unitary circle and be stable. Then if you have delta t squared 4 times epsilon mu, should be less or equal to 1 to get a great stability condition and a less dispersion, of course, with a relationship obviously acquired in the final implementation. Okay. Well, to unify all the dispersion model, we have to analyze the Taylor error, the Taylor numerical error, that is related with the derivative component in terms of any other PDE. As you can see here that this error should be less or equal to 0.2 or 20%. And as you can see, if you substitute the number of derivatives components and delta x or in any spatial domain of the Maxwell PDE, you can arrive to the 14 equation. And this equation is related with this parameter that is ppw. ppw is the points per wavelength in the entire related simulation. That is lambda wavelength over delta s. In this case, delta s is the number of density number of that is related with the number of G cells around each axis analyzed. Okay, and as you can see, if you substitute ppw should be greater or equal of, in this case, with this constant, and this constant could be analyzed in these plot figures. As you can see a behavior that is harmonic distribute, an exponential, another one that is exponential. And if you can see this part, you can see that if you are in the part that is 10 or less percent that in terms of spatial density, you can have less than 0.1 value of dispersion around the final implementation execution. Then you should stay in this kind of part of the figure or less to assure a great result at the end of the simulation. This is the most important part of this analysis. And as you can see in 3D, you can see the if you relate the spatial index, that is the total length of the axis, and if you compare the delta S value, that is the number of G cells per axis, if you have almost one G cell per x-axis, you should have around 70% of dispersion. That is a lot. Then you have to maintain around this kind of zone that represent obviously a great amount of G cells in terms of the length of the entire axis. In this case, the critical axis, of course, that should be X, Y, or Z. And this is the most important analysis for this error. Okay. Well, we have now a dispersion threshold to work around the implementation part, and after this we want to describe the binary models and the Faraday model, that is the broadcasting strategies to do here. And obviously we want to implement this and measure the final results for both. Okay. Then we must start with the binary tree. The binary tree model are described in these schemes. One is the complete binary tree, and the other one is the incomplete binary tree, because if the complete binary tree always have all leaves complete in the last part, and the incomplete obviously are generalized for any other quantity different of power of 2 values. Okay, and if we continue to expand this kind of model, we can describe the number of packets that could be sent per each index in the array as the equation 15. Then the equation 15 is related with the number of processor in the array, that is NP, and the Y number, that is this I number, is the index of the processor that should be sent, and this phi function, that is an adjustment function related with the incomplete binary tree possibility. Okay. Then if we continue this part, this phi function is described in this plot figure. This plot figure is describing the phi function as a function that is adjustment between the complete binary tree possibility. And as you can see, this function is 0 per each value of power of 2 number. Then this function should be taken into account to generalize the entire binary tree model. Okay, and if we continue to expand the model, we can arrive for the communication time, in this case the broadcasting time, that should be spent to implement the binary tree model, or to analyze the binary tree model at the end. Then the TB value are depending on the number of packets that should be sent per each index or per each processor in this case, and it should be multiplied by the machine parameters, that is in this case the transmission latency in seconds, beta, that is the transmission channel bandwidth, there is the bytes per second, and dn, there is the number of packets, or number of byte packets listed. Then if we have the list of binary packets or list of byte packets, we could always divide it by a transmission channel bandwidth. Then at the end, the number of 3 stages that is related with the number of packets should be multiplied with this transmission channel latency, transmission channel bandwidth. Okay. Well, to continue this, we could explain it with these plot figures. In the left part, the A part, is the number of initialization messages that should be sent per each index in the processor ID. As you can see, the number of packages should be sent by a processor 0 is obviously greater than the other ones. And if you go further and further in the processor ID, you should send less number of packages, of course. And if you analyze the generalized model in terms of time, if you increase the number of processors, you should spend more time to do this, but obviously you should see a logarithmic kind of behavior that is related with this phi function that is changing between the power of 2 values. Okay, this is an example for 100 processors. Okay, well, to continue the analysis, we have a parallel execution time binary tree. There is this is equation 17. There is around the best case of initialization, and in the T part of this equation 18, you should have the implementation using the total implementation using the binary model with 2 stochastic values, that is this zeta value and alpha value. They are depending the amount of parallelization part that you could do per each packet that you should send, and what kind of amount of implementation that you should do per each processor meanwhile you are sending package. And this time is the initialization time. Then you should have this entire compound of time that is related with the total time that you should spend using the binary tree. Well, this is the binary tree, and the other one is the Farley model. Then the Farley model is explained here in this chart. As you can see, that the distribution is not a structure that is like a trees or stages in a complete binary or incomplete binary tree, but also it is a structure that is depending on a pathway structure. In this case, the 2D Farley is a structure where the P begins to send almost at the same time in left part and down part, and the other ones should send. If you have processors in the first row, they are always sent left and down, and in the other case or otherwise you should always send vertically. Then this is the particularity of this kind of scheme or broadcast strategy. Then when you analyze this, you could have the 2D Farley model time, or the execution time, the communication time, that is related with each index in the Farley array. Then if you want to arrive to the index ij position in the 2D array, you should have a plus j positions multiplied, of course, with the machine's parameters. And if you have to obtain the absolute position in the matrix, you should have the I multiplied by the number of columns plus j, that is the number of values in the number of rows in this case. Okay, this is the absolute position in the array. To analyze it to the Farley. Then, to analyze this, our main reference to do this is the CEN 2007 article that defines a theorem that is talking about the Farley pattern. As you can see, the Farley pattern gives you the idea that all other index in the array should receive a message by 0, 0 position, exactly once. Then you can assure an unicity inside the 2D Farley array or 3D Farley array, as you can see later. And the author describes here the possibility to talk about a radio kind of number, that is a constant related with the number of processes that should be activated to send a package. As you can see here, this radio for 2D is related to 1 over n. If you have n is the number of rows in the array. If you have this radio mirrored to 1, you should have a broadcasting radio to be better in this case, and we have to enhance it in terms to do more nearer to 1 in this case, but for a 2D case is 1 over n. Okay. Well, for us, we have the extension of this 3D model. There is this P structure that, if you can see, the frontal face of the structure is similar to 2D array, but the other kind of faces in the array should receive only z-axis. This is the difference between the array that you can you see that we analyzed before. Well, to follow this, we define two theorems that are totally related with the beginning of the previous one that was defined by CEN. The theorem 1 is the Farley model, is extension of this 2D Farley model, and you can see we could have a XY plane of the 3D structure is similar to the 2D Farley model, and if we follow the Farley model, all the nodes except 0 and 0 will receive the package exactly once. Then it is an extension of this array, of course. And well, if we extend this, we could have the absolute position similarly, in this case advancing in the array in the 3D structure, and at the end we could have this Farley model time that is a linearity similar with the 2D structure. As you can see, it is multiplied by the machine parameters too. Okay, and we could assure the unicity for the 3D Farley model, of course. As you can see, it is the 2D plot that describes the time variation in terms of the number of processors. As you can see, the critical number of in this analysis is the prime numbers. If we have the prime numbers, we can have the worst threshold in terms of execution, or in this case, the communication time in the filing model. If you can have the most factors you can have, you could have a lower threshold in the entire broadcasting time description of the model. And as you can see, there's a theoretical estimations of the speed up. If you have some variations in terms of theta or alpha values in terms of binary tree, we could have a binary tree best case. Or if you increase this number of theta or alpha values, you could have another average case that is worse than the other one. Then this behavior should be maintained in the total scheme of the binary tree in this case. It's an estimation. And this other estimation is for the filing model. As you can see, the speed up taking into account the prime numbers is lower than the speed up that is taking into account for the custom person numbers, of course. Okay. Well, to describe the problem in detail, we have to take into account that each processor in the 3D structure should have this approximation. This yellow cube is about the computational domain, that is regular cavity rounded by the PEC, and the gray cube is the number of cells that are equally distributed inside the regular cavity. All these cells should have an amount of G cells that is a most basic unit of the FDTD array. And this structure should be defined in the MPI description at the end. And this structure is the processor cell, or the gray cube here, that obviously is shown the 6 neighbors that should be taken into account in Y, X, and Z axis, 2 per each axis. Okay, this is the basic description of it. And to describe it in detail, first we have to take the sequential description. As you can see, if you solve the binary the FDTD of only one processor, you could have, if you extend the number of G cells, you could have a polynomial kind of behavior. And if you extend the number of FDTD time of time stepping, you should have linear behavior. Then the number of execution time is a little bit considerable in terms of the parallelization part that you could acquire using another kind of parallel broadcasting strategies. Okay. Then, to complement this is another measurement. This is a measurement of broadcasting time in terms of binary tree. As you can see, it's a log behavior that is changing between the power of 2 values. As you can see, the power of 2 values represent a lower case in all the other measurements. In this case, to 64 maximum kind of processors. And this is the Farley model. As you can see, it's a linear in terms of approximation. As you can see, the prime numbers represent a worse code or worse threshold, and the custom numbers represent a lower case. Then you could have a similar behavior with the theoretical estimation that was explained previously. Okay, following this, you could measure the possible speed up taking into account the 2 models, the Farley model and the binary tree model. As you can see, the Farley model could be extended more as the binary tree one, because the binary tree one, in terms of the stochastic values, represent the worst quote in this case, and the Farley model could be analyzed with more quantity of processors. In this case, we could arrive to 5 or 8 processors and obtain a 20 speed up amount that is important in case of implementation. Okay, but obviously it is depending on directly with the machine parameters. Then, if we have a switch one case, we could obviously have no more advantage at the end of the implementation. Is the most naive kind of case. Okay. Well, and obviously to obtain the complete part of the execution, we could measure the time using by execution, that is the blue one, and the time that is used by the Farley, and the time that is used by the binary tree. As you can see, the binary tree is a little bit more regular, but is higher than the Farley model. That is more regular, but has some lower case that are depending on the custom number of processors that is not these kind of peaks that are depending on the prime numbers, of course. Okay, and at the end we could have the time fractions in terms of parallel time and broadcasting time per binary tree and Farley model. Then per binary tree you could have that the initialization or broadcasting time is obviously greater than the execution time, and in terms of Farley model the number of the or the reason of in the total amount of time or the percentage is more balanced, and it is obviously a great result to take into account. Well, we arrived for another kind of implementation that is the FDTD MPI This block is around a draft of FDTD engine around the stepwise implementation of FDTD value with some max and some registers that give us the possibility to get a feedback in terms of multiplication or addition kind of operators inside the FDTD value. This is the most important in terms of the FDTD. And these routers here are obviously limited us to get an approach or advantage approach in terms of FDTD implementation, but obviously give us the possibility to decrease the number of EO blocks at the end of the implementation. Then, if we measure these area blocks, you could have the most critical kind of blocks is the number of memory RAM blocks. That obviously for the Vertex 5 is this kind of constant threshold for us is obviously the most critical one. But the implementation that is measured in MPI is obviously possible because it is lower than 10. But give us the possibility to work well in terms of the MPI approximation. And well, at the end we could analyze the final EM results. That is one is the most important part in the thesis description. There is this regular rectangular cavity with one electric source, that is electric dipole, and one observer. Then this is the description of this cavity specifically. All the quantities in the spaces in millimeters. The time dimension is in seconds. As you can see, the cavity size in this case is 20.5, 16.5 in Y, and 7.5 in theta. And the infield dipole is spread in the lower part is this green point, this in the same figure, in the previous figure. The amplitude of this E-field dipole source is 1 ampere per meter for a square meter, and it's a Blackman-Harris window with order derivative. And the observer is spread upon the source. That is this blue point in this cavity, this custom cavity. As you can see, all the material is rounded by PC, and the internal material, the inner material, is a resonant material that have one relative permeability and two electric permittivity relative in both cases. Then the values in the conductivity should be 0, as we can talk previously, to neglect the attenuation behavior at the end. Then, to complete the time length, we have a total time that is 2 nanoseconds and a maximum time step that is 1 picosecond. Okay, that is the most important case. We could have 2,000 time steps for the complex simulation in this example. Then, as you can see, these are the entire implementation for EX and EY fields. As you can see, for our customs EM simulators that are MIP, Octave, Open EMS, and WCT, we could have the same behavior in X and Y. That is a great result for us. It is in any field that is volts per meter. And as you can see here, there is the theta and HX fields. As you can see here, we could have a similar behavior per MPI to Octave, MIP, Open EMS, and so on. Okay, and the Fourier transform is totally similar, and you can obtain obviously a lower error in terms of the final implementation. And as you can see, this is the error in terms of time. As you can see, the error has a maximum kind of threshold over 10% in the worst case, that is the E zeta field. And in terms of Hx or Hg is the same one. Okay. Then to make a compound of these errors, we could have this approximation, that is these errors that are so low in terms of octave comparison, or in the WCT comparison, that is the best approximation or the best simulation for us. MIP and OpenEMS are open source, but not so good in terms of the other kind of approximations, but it is obviously plain FDTD kind of implementation, for a kind of algorithm inside of MIP or inside of OpenEMS. Okay, and at the end we have the conclusions. You can have conclusion that is related with the number of processors. In terms of value, we could have with 5 or 15 processors for the MPI, taking into account the stochastic parameters, as you can see in the speed up plot chart. 3D mesh computational scheme is a disadvantage in terms of the worst case scenario in MPI, and obviously are totally depending on the machine parameters. The dispersion error is obviously critical to establish a constant threshold or a constant range to get a great implementation without dispersion and instability conditions. And CNN is so flexible to get any other kind of broadcasting strategies to get started in the future. Okay. And the filter works, we could have an implementation in FPGA, making it move deeper and deeper and matches with a theoretical model. And we could develop some application using lumped elements or other kind of physical structures that are more complex than the resonant cavity. Okay, this is the end of the slides, and thank you for your attention. This is the bibliography that should be studied to give this. Thank you so much.